So this morning what I'll present on is a few slides on what the future uranium mining projects will look like. And a bit of an overview of the talk this morning. So before we get into what the uranium mines will look like in the future, I'll take a few moments to talk about global uranium demand and supply. And then we'll look at an overview of global reasonably assured resources, and I'll define what that means in upcoming slides. Then we'll get into a little bit more detail, and we'll talk about the geological summary of the above noted resources from a global perspective. And then we'll start talking about and present on the grade and tonnage, the structural geology and the mineralogy and geochemistry of various uranium deposits around the world and resources. And then look at some mining and processing considerations, both technical and economic. A majority of my presentation this morning will be coming from information from the IAEA NEA Red Book. The Red Book has been published since 1965, and it's a joint report that's been published by the NEA, OECD, and the IAEA since 1969. It's widely recognized in the international uranium community and nuclear community as a primary reference document on world uranium supply, demand, and production as well. And I'm happy to note that it's available as a free download, and I've provided the web link on the presentation as well. So the source of the information for the Red Book comes from member states' survey questionnaires, as well as the Secretariat reports and various estimates from experts. It's published every 2 years, and it's published on alternate years from the World Nuclear Association's Nuclear Fuel Report. And the next edition of the Red Book is in progress and will be published in 2020. So this slide highlights the uranium demand forecast taken from the Red Book, and I'd like to draw your attention to the top 2 lines on the presentation. So these 2 lines here are the ones that provide the global forecast for the low case and the high case. And currently there's 449 operating reactors globally, producing about 391 gigawatts of electricity. This requires about 63,000 tons of uranium on an annual basis. And in the low case scenario that's presented on the graph in the dashed line, shows a decrease in uranium demand by about 15% to around 331 gigawatts of electricity. And the reason why we see, or we forecast a decrease in the demand for uranium with this downturn in the industry is there's a phase out of nuclear power in various countries, as well as some member states are considering moving into nuclear power, but haven't formally committed. So there's some uncertainty around that too. So there's the low case scenario. The high case scenario, alternatively, shows an increase in global nuclear power production from 391 gigawatts of electricity to 568 gigawatts of electricity. So in the high case demand, there's an increase for uranium of about 30,000 tons annually. And the highest growth areas for nuclear power are Asia and the Middle East, and we see moderate growth in Africa and South America. And at present, there's 59 nuclear power plants under construction, with several countries considering new builds of nuclear power plants. So this graph highlights uranium production capability versus demand. And in 2017, primary production provided about 95% of world requirements. The remainder of the production came from secondary supplies, which includes excess government and commercial inventories, spent fuel processing, and also downblending of highly enriched uranium. So if we take a moment to have a look at this graph, the dark blue lines here represent actual global production. And for my previous slide, This represents the high case demand scenario and the low case demand scenario. The light blue lines here represent nameplate capacity of all global uranium operations. So this is actual nameplate. And then if you can see the lighter gray bar here, that represents the forecasted increase in uranium production. So meeting the high case demand requirements to 2035 would consume less than 25% of the total identified uranium resource base. However, significant investment and technical expertise will be required to bring these resources into the market and into production. Producers will have to overcome a number of significant and at times unpredictable issues in bringing new production facilities on stream. This includes geopolitical and local factors, technical challenges, and legal and regulatory framework. In addition, strong market conditions will be fundamental to bringing the required investments into the industry. So the second graph that I show here represents 85% of forecasted nameplate production capability achieved, which is in keeping with what we've seen in the past. So if we see here, this is 85% of current nameplate capacity, and then also in the light gray bars is 85% of nameplate capacity achieved. So with that, we could see a potential shortage of supply of uranium beginning in 2027. So this graph highlights the spot price and the long-term and short-term pricing for uranium on a global basis. And as the graph here I've highlighted from 1982, and the data in the red book goes up to 2016. So from 1982 to about 2002, we saw a steady decline in the price of uranium. And then in around 2006, 2007, we saw a sharp increase in the price of uranium at a time what was called the nuclear renaissance. Then in 2011, we had the incident at Fukushima Daiichi, and we've seen a steady decrease in the price of uranium. There continues to be a decline in the uranium spot price following the Fukushima Daiichi accident and lingering uncertainty about nuclear power development in some countries. This has temporarily reduced uranium requirements, thereby further depressing the price of uranium to its current price of around $25 US per pound. These market conditions have slowed the pace of new mine development and have forced several operations globally to reduce or stop production. So this image, we start to look now into the resources around the world, and this is a global distribution of identified uranium resources. And this image here, this figure here, represents recoverable uranium at less than 130 US dollars per kilogram. So in this diagram, we see 15 countries represent 95% of the identified global resource base in this cost category. The remaining 5% are distributed amongst 22 other countries. So the top producing countries, which are 5 of them, produce about 80% of global production. And what I've highlighted in this image here is the top 4 resources globally. So we have Australia, which has the most abundance of uranium globally, and they are currently producer number 3 in the world. We have Kazakhstan, which has the second greatest amount, and they're currently number 1 in terms of annual production capability. And Canada has the third most resource, and they are currently producer number 2. And Russian Federation has the 4th greatest amount of resource and is currently producer number 6. 2 of the other larger producers globally are Namibia and Niger. So this image represents the 12 top countries for uranium resources, as shown in this graph. So if we look at the identified global resources at a recoverable cost of $260 or less than $260 per kilogram, that's estimated at 4.8 million tons of uranium. The total identified resources as of January 2017 amounts to 6.1 million tons of uranium. So we see the top 12, as mentioned earlier. We have Australia, Canada, Kazakhstan, Namibia, Niger, Russia, South Africa, Brazil, India, Ukraine, China, and the United States representing the top 12. If we look at the anticipated production methods, starting to look at what the mines will look like in the future, based on those global uranium resources, we see this pie chart here representing that distribution as percentages. So if we look at these percentages in decreasing order, we see co-product, byproduct at around 32%, and that represents primarily the Olympic Dam operation in Australia. Next, we have underground mining. The northern Saskatchewan operations, for example. Open pit operations, again into Canada, Australia, Africa, and so on. And then we have in situ leaching by acid, which would represent Kazakhstan, and then in situ leaching by carbonate or bicarbonate as the least represented. And then unspecified coming in at around 2%. So you see that it will be dominated by a mixture of ISL, underground, and open pit as the main sources of production. This graph looks at the distribution of current world uranium production by production method. So annual current productions, and once again is distributed by percentages. You see that the highest percentage of uranium production is by in situ leaching, represented by Kazakhstan, China, and others. Next, we have underground mining, represented by McArthur River, Cigar Lake, and others. The co-product byproduct, which of course is Olympic Dam again, representing about 16%. And we have open pit mining here in the blue at around 14% of uranium production. So far in the presentation, I've been talking about conventional resources. So conventional resources, as defined by the Red Book, are resources that have an established history of production where uranium is a primary product, a co-product, or an important byproduct, such as mining of copper or gold. There's also another resource that's called unconventional resources that can be quite important as we go into the future in particularly, and they're defined as very low-grade resources or from those which uranium is only recoverable as a minor byproduct. And those examples include phosphates, black shales, coal, and heavy mineral sands. So if we look at unconventional resources globally, based on the Red Book, it shows that there's 28.5 million tons of uranium available as an unconventional resource, and you can see the breakdown there on the pie chart. The UDEPO database, which is a IAEA database for uranium deposits around the world, estimates unconventional resources at around 45 million tons of uranium. And the difference being is the Red Book represents uranium that's known and is recoverable, and the UDEPO database represents all uranium in resource material. So Morocco has the highest reported phosphate resource in the world, with over 6.5 million tons of uranium. Iraq also has significant uranium resources of 700,000 tons of uranium bound in phosphates, and Sweden has around 1 million tons of uranium bound in black shales. So market conditions and technological development will be the main factors that will determine the contribution of unconventional uranium resources to world production totals in the future. As well as I mentioned earlier in the presentation of the global map, and the top 6 producers produce over 95% of the annual uranium. There is a growing concern about security of supply, and we see a lot of member states or countries now looking at that as an issue and looking at unconventional resources as a means of security of supply as well. So if we look at the global resource by deposit type, this graph represents both the conventional and the unconventional resources. And it's defined, or this graph is represented as reasonably assured resources. And the definition of that is uranium that occurs in known mineral deposits of delineated size, grade, and configuration. These reasonably assured resources have proven mining and processing technology, and the grade tonnage is well understood based on specific sample data and measurements and knowledge of the deposit. So if we walk through some of the major contributors in this graph from top to bottom, the phosphate deposits, they're typically marine-based, usually bound in phosphate-bearing apatites, and significant resources of phosphate ore, but very low grades, typically around 50 to 150 parts per million. And as I mentioned, US, Jordan, Morocco, Egypt, Iraq are the main deposits of phosphates. Next are the surficial deposits. They're near-surface uranium concentrations in sediments and soils. They're mostly calcium and magnesium hosted. And a couple examples of these are the ULIRI deposit in Australia, as well as the Langer-Heinrich deposit in Namibia. Next in line is the metasomatite, and they're confined to Precambrian shield areas. The Ukraine and Russia have these types of deposits, and they're typically deep granite-hosted deposits. Next we have intrusive, which are igneous-based host uranium. And in Namibia, there's a couple examples at Rossing and Husab, as well as in Greenland at the Kavenfeld deposit. Finally, we have the polymetallic iron oxide breccia complex, which are iron oxide, copper, and gold deposits. Olympic Dam is a good example of that, with greater than 2 million tons of uranium resource in that category. The sandstone deposits, they're uranium precipitated sandstone under reducing conditions. Russia, Australia at the Beverly operation, the Czech Republic, Niger, Kazakhstan, US, and Gabon are examples. And the typical grade in the sandstone deposits range from around 0.1 to 0.5% uranium grades, but sometimes as high as 1% U3O8. And lastly, we have the unconformity deposits. And the 2 main districts, of course, are in Canada in the Athabasca region and in Australia at Kintyre, Jabiluka, Ranger, and the Pine Creek, Oregon area. These deposits are significant, with up to 200,000 tons of uranium and grades ranging between 1 to 20% U3O8. So this diagram was provided by my co-author and colleague, Dr. Martin Fairclough, and it's a diagram that's from the IAEA UFO Database. I just want to take a moment to talk about this. We have the grade tonnage curves here, so it's on a logarithmic scale, and we see the grade on the y-axis and the relative tonnage on the x-axis. So the first circle that I've highlighted in the top right-hand corner is the unconformity type deposits. We see they're fairly high grade, and Canada and Australia have a couple examples of that. Next is the sandstone, with Russia, Australia, Czech Republic, Niger, Kazakhstan, US, and Gabon. And lastly, highlighting the polymetallic iron breccia complex, which are the 3 main areas of uranium production on a commercial basis right now. Overall, the highest grade uranium deposits are dominated by unconformity-related deposits, as found in the Athabasca and Northern Territory of Australia, and are particularly the unconformity contact subtype. Now, this information from the UDEPO database is well summarized in this world distribution of uranium deposits. It's an interactive PDF map that was created by my colleague, Dr. Martin Fairclough, and colleagues with the IAEA. And it's quite an interesting map, and it shows all of the uranium deposits by subtype. And as I mentioned, it's very interactive, so you can turn on and turn off different layers. I encourage everyone to download it and have a look at it. So if we look at world production capability forecasting out to 2035, the Red Book suggests this possible scenario where we see, first of all, on the bottom of the x-axis, we see existing and current capacity out to 2030, existing and current capacity plus future development out to 2030, and similarly existing capacity out to 2035, and then existing capacity plus future development out to 2035. So we see Australia looking to ramp up, Canada looking to ramp up and become still being major producers, as well as Kazakhstan. If we look into Asia, China will be producing, the Ukraine, Russia, as well as Uzbekistan. United States is forecasting to restart operations. And in Africa, we see that Namibia and Niger will continue to be major players in the uranium portfolio as well. So what are some of the key considerations as we look into mines of the future? So obviously geology, mineralogy, and geochemistry will guide the mine design and process flow sheet. And as we see the uranium deposits moving into the future, lower grade deposits will dominate global resources. And according to the Red Book, concludes that processing costs for about 60% of conventional uranium resources will be greater than $130 US per kilogram. Also, I thought it would be important to note where these deposits are geographically located, that water is an important commodity in several of these uranium-hosted countries, and water management strategy is essential. One of the challenges with these uranium deposits is the long lead time, typically 15 to 20 years to bring them into full development, and as noted earlier, may result in a shortage of supply in the near term. And if we look at future mining and processing considerations based on geology and mineralogy, for commercial uranium production, the future will be dominated by in situ recovery. And as defined on the grade tonnage diagram that I presented a couple slides ago, the main uranium-hosted deposits in the future are sandstone and unconformity type deposits. So what are some innovation opportunities in the uranium industry as we move forward? One of the greatest opportunities will be to reduce mining costs. So we're starting to see some innovation and moving forward in the industry with the application of in situ leaching in unconformity type deposits. And we see an example of that currently with the feasibility study going on right now in northern Saskatchewan with Denison Mines at their Wheeler River project in the Phoenix deposit. And what is being identified with the application of ISL and unconformity type deposits is they have a similar structural geology and geometry to the sandstone deposits. The freeze wall technology has been well developed and is typically, or is possibly or forecasted to be applied around these types of deposits to confine them. One of the challenges with applying ISL and unconformity type deposits is that the higher temperature of formation, which could result in potentially different extraction chemistry, could be more challenging to extract the uranium from these unconformity type deposits. Another application we're being investigated for reducing mining costs is stope or block leaching, and also preconcentration or beneficiation of the mined ores, either by physical or chemical means. Also advances in heap leaching technology for low-grade ores, and we have a presentation coming up this morning on that subject, And also Alan is leading a short course on that subject as well, and application of heap leaching. Also too, I thought it would be important to note that when you're looking at the feasibility or a clean sheet approach for a uranium project, it's very important to look at innovation in the full life cycle as well, such as considering mine closure at the very beginning of the operation and looking at your options while you have that clean sheet in front of you. In terms of security of supply for uranium for different countries around the world, some innovation opportunities that are also happening in the uranium industry are looking at recovery of uranium from unconventional resources and resolving that potential security of supply issue. We're seeing some advances in advanced chemical separation from uranium from phosphate ore. And one of the examples is looking at going from the dihydrate to the hemihydrated form of recovering uranium from phosphoric acid. We're also seeing advances in uranium recovery from monazite and xenotime minerals that are sourced from either tin tailings or black sand material for the recovery of uranium, thorium, and also rare earth elements. So some comprehensive extraction. Some recent IAEA publications that are relevant to uranium mines in the future. We have the Undiscovered Uranium Resources Tech Doc, also the uranium resources as and byproduct, polymetallic, base rare earth, and precious metal ore deposits. And also the geological classification of uranium deposits and description with selected examples. And finally, the UFO Database tech doc. I've brought some copies of these tech docs and also a paper copy or a hard copy of the world distribution UDEPO map. I've left them on the sponsorship table, so if anybody is interested in these tech docs, please help yourself to those copies that I brought. Also, they are available free for download from the IAEA website. In summary, global uranium demand is expected to continue to increase in the next several decades due to large population needs for electricity and a growing middle class who have increasing electricity demands. Nuclear power plants produce competitively priced, low-carbon baseload electricity, and the deployment of nuclear power enhances the security of energy supply, and it is projected to remain an important component of energy supply globally. However, sufficient resources are identified, but pounds in the ground do not equal pounds in the can. So it's important to note that innovation is required to make low-grade deposits economical and technically feasible. As many member states around the world look at their energy policy and strategy, security of supply is a key strategic consideration, and it may also drive innovation for the recovery of uranium from unconventional resources. And once again, in concluding, advances in recognizing waste issues early in the life cycle is very important. I would like to acknowledge my colleagues from the NEA and OECD, as well as colleagues from the IAEA and the IAEA Uranium Working Group members who contributed to the Red Book publication. I thank you for your attention. Thank you.
We've got time for a couple of questions, if you have any questions for Brett. If you have, just come to the microphone and give your name and affiliation. Anyone? Yes, we have one.
Hi, good morning. Is this on? Yeah.
Yes,
AJ Gerbino, OLI Systems. Just two questions about the quantification. One is you talked about lignite coal. Mm-hmm. Does anthracite and bitumen also fall under the same, bituminous coal also fall under the same category? And would fly ash also be a resource as a result of that, cold burn fly ash?
The answer to that is yes. So coal is generally considered with all those metallurgical and bituminous coal as well. Yeah. And fly ash is, of course, a byproduct of coal-fired power plants, yeah, would be considered as a potential resource. In particularly in the UDEPO database, fly ash is considered there.
It is, okay.
Yes.
And just one other question.
Please.
The plot showing, I guess, that leach type of mining with the sandstone, I mean, if you could actually pull that right out of an oil and gas production manual, because they'll do polymer flooding. So my question, therefore, is to what depth did you study the reservoirs or the resources? Because sandstones, they can go 4,000 meters, 5,000 meters deep.
Right,
Yeah.
right. Well, current uranium production with sandstone mining for in situ leaching, typically to a maximum of a few hundred meters at this particular time.
So there could be much more further down than, is that fair, or?
That's fair to estimate at this point, yes. Yes, thank you for the question.
I think we'll have to leave further questions until, just for the sake of time, till the break. Of course, Brett will be available throughout the day for you to answer questions face to face. So let's just thank Brett very much.